Put the cover of the modulated cubic surface.
Okay, so maybe we can start. Okay. So it's our pleasure to have Professor Michael Hutchings from University of Berkeley, and he will talk about periodic orbits of vector fields in 3 dimensions.
All right, thank you very much for the invitation. People joked about the weather here, but actually I have terrible spring allergies in California, which are already starting. So this is a wonderful break for me. Okay, so the setting for this talk is why it's a compact three-dimensional manifold. And there isn't really any topology in this talk, so you can if you don't want to think about topology, you can just consider the case where it's the three spheres, it's just R3 with an extra point. And V is a smooth vector field on Y. P is a point in Y, then we have a vector at the tangent space at F. So every point is a vector, and we're interested in dynamics, and one of the simplest things you can do with dynamics is to look at trajectories of the vector field. You start at some point and you move in time, and at any time your velocity vector is the vector v at that point. And you say, okay, what's going to happen? And one of the simplest, well, that's dynamics. And then one of the simplest questions you can ask is, well, can you ever start at some point and follow this vector field for some finite amount of time, and then come back where you started? So periodic orbit is a smooth map gamma from R mod Tz to Y for some t greater than 0, which is the period such that gamma prime of t is v of gamma of t for all t. So that's a periodic orbit. It's a loop in the three manifold. After time capital T, you come back where you started. And there's some pedantic things to say, so I don't really care exactly where you start. So if I start somewhere else in the same loop, I think of it as the same periodic orbit.
I guess you want the map to be injective, right?
Yeah, so I actually, not necessarily, so I say it's simple.
Then the period is not well defined, is it?
Yeah.
Sure is.
So I say it's simple if gamma is injective. So period, okay, maybe it's not the best word for it, but in any case, if gamma is injective, then capital T is the minimum amount of time to come back where you started. Gamma is not injective, you go around the same loop some number, positive integer number of times. So capital T, well, it's a period, it's not the minimum period. Right. So then, some basic questions. So, periodic orbits exist. And if so, what are their properties? Well, it's pretty easy to make examples of vector fields with no periodic orbits, although it's actually pretty difficult on S3. So for any three-dimensional manifold, there exists a vector field V. With no periodic orbits. So an easy example is where Y is the 3 torus, which is R3 on Z3. So it's just a cube where the opposite faces of the cube are identified. And then you could take the vector field to look like V equals A d by dx plus B d by dy. So that the coordinates are x, y, and z, where A over B is an irrational number. Okay. So it doesn't move at all in the z direction. But on an xy slice, the vector field looks like this. So vectors are all sort of the same at every point up to translation, but it's some irrational slope. So you start at some point, you're never going to come back to the same xy. So
Are you assuming in the discussion that V is nowhere 0?
yeah, sure. If V is 0, I guess you have like a constant periodic orbit at a point.
No, yeah, but like you don't want to consider it.
No. And soon I'm going to get to Reeb vector fields, which are always non-vanishing. So constructing examples on S3 is hard. So there's a whole history of this problem. It's called the Seifert conjecture. I don't remember if the conjecture is that there always is a periodic orbit or if it doesn't have to be, but in any case, it was resolved in the smooth case after various history with less regularity by Christina Cooperberg. In the 1990s. So examples do exist. Now, yes.
What's the point like that the S3 is a Lie group is like there are no translation invariant examples, and that's sort of why constructing them is hard. Like this example is translation invariant.
Right. Yeah, I mean maybe there's some easy way to do it, but nobody has figured it out. So the constructions involve, well, you can make an example with just a couple of periodic orbits, and then they insert something called a plug. So basically you insert something or in the neighborhood of a piece of the orbit, which does something very complicated, which destroys that orbit without making any new ones. And it's very hard to make this plug smooth. Now, if we make some more assumptions on the vector field, then periodic orbits always do exist. And exactly what assumptions you need is a deep philosophical question. Like it's still an open question whether or not every smooth, volume-preserving vector field on the 3 sphere is a periodic orbit. It's okay. So the vector fields that I'm going to talk about today are called Reeb vector fields. So they start with the contact form. So recall that. The contact form on our 3-dimensional manifold is a 1 form lambda such that lambda wedge d lambda is no to 0. If you've never seen this before, I'll give you examples in a minute. And then lambda determines the wave vector field R, and it's characterized by two equations. So first, d lambda of R comma anything is equal to 0. So this equation tells us that d lambda is a non-zero two-form. So that means on a three-dimensional vector space, it's going to have a one-dimensional kernel. So up to scaling, there's a unique vector R at every point satisfying this property. And then to fix the scaling, we say that lambda of R is equal to 1. So that's the Reeb vector field. Then there are two basic examples. So the first one, so let Y be a compact hypersurface in R4, which is transverse to the radial vector field. In symplectic geometry, we call these star shapes, which is a slight misnomer, but the condition I'm assuming implies that the compact four-dimensional domain bounded by Y is a star-shaped set. So, picture. So here's R4. I have my hypersurface Y. If I draw any ray starting at the origin, then it's going to intersect Y transversely. It will not be tangent to Y. So that's a star-shaped hypersurface. Now, let H be a smooth function. Such that Y is a regular level set. H. So Y is a level set, and on Y the derivative of H is not equal to 0. And then this determines a Hamiltonian vector field. So well, any smooth function on H determines a Hamiltonian vector field. That's H. So if my coordinates on R4 are x1, y1, and x2, y2, then up to sign conventions, this is sum of dh dxi d by dyi minus dh dyi d by dxi. Actually, I think I want the sign squared that way. And then in Hamiltonian mechanics, if the x1 and x2 are position coordinates and the y1 and y2 are momentum coordinates, then classical mechanics says that if your point in R4 represents a state of a physical system, then it will evolve in time by following the trajectory of this vector field. And then the claim is that in this situation, then the Reeb vector field is parallel to xh restricted to 1. So the Hamiltonian vector field is tangent to any level set of H. So if you start on a level set, you stay in the level set when you follow the vector field. And then up to scaling by some function in y, this is the Reeb vector field. So periodic orbits of the Reeb vector field are equivalent to periodic orbits of the Hamiltonian vector field in y. You'll just be moving along them at a different speed. So you could be going around the same road, but maybe you're driving faster or slower. So if you're interested in periodic orbits in Hamiltonian dynamics, then that's one reason you might be interested in Reeb vector fields. The second basic example that sigma is a compact surface. And G is a Riemannian metric. On sigma, and then there's a canonical, and y is a set of unit cotangent vectors. So the metric gives you an identification between tangent vectors and cotangent vectors. So you can think of these as unit tangent vectors. So these are tangent vectors that have length 1 with respect to the metric. So this is now a 3-dimensional manifold because at every point on the surface there's a 1-dimensional circle of unit tangent vectors. And this has a canonical 1 form. So there's a canonical 1 form on the cotangent. On the cotangent bundle. Actually, there's a canonical 1 form in the cotangent bundle of any smooth manifold. So basically, in local coordinates, so Q1 and Q2 are local coordinates on the surface, and P1 and P2 are the corresponding local coordinates on cotangent vectors. Then this 1 form is so from I equals 1 to 2 pi dqi. You can also say it in a nice coordinate-free way. So it's this canonical 1 form on this 4-dimensional cotangent bundle, and then it's a fact that lambda restricted to y is a contact form, and then the associated Reeb vector field coincides with the geodesic flow. So it's the vector at any point in the unit tangent bundle. It points you in the direction of that of the geodesic at that point. So so that implies that periodic orbits of R correspond to oriented closed geodesics. And they're parametrized at unit speed. So on the surface, a geodesic is just it's just some curve which minimizes length. And then, well, you can go around this curve in one direction or the other. That's two different Reeb orbits because in the unit tangent bundle you have opposite tangent vectors. So if you like geodesics, that's another reason to be possibly interested in Reeb vector fields. Is there any questions about these definitions? All right. So let's take some theorems. So theorem of Taubes. 2006, which says that for every contact form on a closed three manifold, there exists a, so I'm going to call these Reeb orbits, so Reeb orbit. So this Reeb orbit means a periodic orbit of R. So there's always at least one. And this is the three-dimensional case of the Weinstein conjecture. So the notion of contact form and Reeb vector field has a generalization to any odd-dimensional manifold. So the Weinstein conjecture says that any contact form in any compact odd-dimensional manifold has a periodic orbit. So this is known in the three-dimensional case by Taubes. There are various earlier results by a number of authors, or for others, proving this in some cases, but Taubes give so far the only known proof in all cases in three dimensions, and uses very non-trivial Seiberg-Witten theory. The Weinstein conjecture in higher dimensions is mostly an open question. Okay. So, anyways, so I don't know what exactly you need to assume about a vector field to guarantee the existence of periodic orbits, but being a Reeb vector field in three dimensions will do it. Okay. So now you could say, all right, well that's very nice. But if you try to make examples, you actually usually find lots of Reeb orbits. They're sort of like weeds, like you pull weeds and then other weeds sprout up. It's really hard to get rid of all of them. So then, you could try to improve on this result. So with my student, Dan Christopher Gardner, and myself, and this makes crucial use of another result which we proved with Vinicius Ramos, which was around like 2013 or 12 or something, I forgot exactly. There are always at least two Reeb orbits. I'm putting simple here because for any Reeb orbit, there are infinitely many multiple covers of it. I don't care about that. But there are at least two sort of Reeb orbits which are different loops in the three manifold.
To prove something like that, is there a way to do it starting with tabs as a black box, or do you have to like dig in and? You said that's the only known proof for one. So is your proof like improving the methods, or is it like doing some clever thing? You apply it again, you take out that orbit. I don't know.
So we had to dig into tabs black box and make some unauthorized enhancements. But I'll sort of tell you sort of a little later the sort of more recent version of that technology. There are some ways in which sometimes there are situations where if you have some periodic orbits with some conditions, there have to be more. I can state some of those results later. All right.
Michael, are there cases where you know infinitely many?
Yeah, in fact, usually they're infinitely many. I'll say the results about
generic or?
Generically, they're infinitely many. I'll say the results about that shortly. Before I get to that, though, I'll mention that, given this, you can say, all right, my next batch of grad students, I should ask them to prove that there are three Reeb orbits. But that won't work because there are examples with exactly two. So example, so if A and B are real numbers, so positive real numbers, and A over B is irrational, we define the ellipsoid. So this is a three-dimensional ellipsoid in four-dimensional space. So my notation is EAB is a solid four-dimensional ellipsoid. Y is its boundary. So this is the set of points Z and C2. So I'm identifying R4 with C2 such that pi times the absolute value of C1 squared over A plus pi times the absolute value of C2 squared over B is equal to 1.
Do you want to square a, oh, they're positive, sorry. Think about it.
I could square them. I have, this is a slightly wacky convention. It's like in symplectic geometry, B of R is a ball where such that pi times the radius squared equals R. That's a little weird. Okay. Right, so then so this is an example of a star-shaped hypersurface like that over there. You can take this function to be the Hamiltonian, so that's a level set of this function. Then you can just calculate what the vector field is. And you find that the Reeb vector field is 2 pi times 1 over A d by d theta 1 plus 1 over B d by d theta 2, where theta k is the argument of zk. So this vector field rotates the complex numbers z1 and z2. It takes time a for z1 to go all the way around, and it takes time b for z2 to go all the way around. So there are exactly two simple Reeb orbits. So gamma 1 is where Z2 is equal to 0. So you just have Z1 as absolute value, whatever it has to be, and then it rotates around with period A. And use gamma 2, which is where Z1 is equal to 0, and this has period B. And then on the rest of the ellipsoid, if you start at any other point where both Z1 and Z2 are not equal to 0, there's no way you can get back to where you are. It's just like the torus example earlier. So that's it. So the only two simple orbits. You can also make related examples on a lens space. So you can take a quotient by a Z mod P action to obtain similar examples on lens spaces. But those are almost the only such examples. So, so this theorem, so this is with Dan Christopher Gardner from before, Umberto Reeb, myself, and Reeb. And then it builds on earlier work with myself and Todd's. Which says that let Y be a closed 3 manifold, and lambda a contact form with exactly 2 simple Reeb orbits. Then Y is diffeomorphic to S3 or a lens space. And there's various numerical data like the periods and some other things like contact volume and rotation numbers and so on. You can read the precise statement in the paper. To be imprecise, I'll just say that, and all numerical data agrees with the above examples.
You think they're kind of conjugate?
So not necessarily conjugate. So there do exist examples of contact forms on the S3 with exactly 2 Reeb orbits, but where the flow is ergodic or more or less ergodic. Is related to examples of catalog, so they're not conjugate. So you could call these sort of like contact pseudo-rotations. But all the other data is the same. So these are sort of mostly all the examples. Other questions about that? Oops.
Okay. So impossibility of you have the impossibility of just one such orbit. So
That's right.
are there other numbers that are impossible? Is it-
Yeah, I think every number which bigger than 2 and less than infinity is impossible. And that leads us right into our next result. I did not plan all these questions beforehand. So there's a theorem, which is the same authors as the previous one. So let Y be a closed three manifold. Lambda contact form. We need one hypothesis, which is the contact structure. So this is a rank 2 vector bundle, and it's oriented, so it has a first Chern class. So assume that this has torsion first Chern class. So this is automatically true if Y is a rational homology sphere. So if all you care about is S3, it's also true for the cotangent bundles of surfaces that we talked about. So then they're either two or infinitely many. Simple Reeb orbits. So at least under these hypotheses, most numbers are impossible. This generalizes a work of Fulfer-Wysocki-Sanger from a while ago, who proved this in S3 under some slightly stronger hypotheses. Without the assumption this is known if lambda is non-degenerate. So I don't have time to say what that means exactly, but this is something which holds generically. And this is by Colin, Deroy, and Russian. So it's still an open question. If lambda is degenerate and if the first Chern class is not torsion, then that's still an open question. Now, generically, you can actually say more than this. So there's a theorem by Erie, which I think is 2015, which says that, so let Y be a closed three manifold. So for a C infinity generic contact form, the Reeb orbits are dense in Y. So that, of course, implies that they're infinitely many. That's a stronger statement. Then the key step in proving this is Fourier's strong closing lemma. So basically, roughly speaking, to prove this theorem, we want to show that starting from any contact form, I can perturb it a little bit to make the Reeb orbits dense. So what you have to do is you want to start with some small neighborhood in Y and make some small perturbation of the contact form in that neighborhood to make the Reeb orbit appear going through that neighborhood. And so figure A proves the following. So for lambda be any contact form in Y, let f be a smooth function which is greater than or equal to 0, and it's not identically 0. Then there exists a number t in the interval from 0 to 1 such that the contact form e to the tf times lambda has a Reeb orbit intersecting the support of f. So let me draw a picture to explain what's going on here.
So it's like the opposite of a flow plug, like of a Cooperberg flow plug.
Right. We are trying to encourage the weeds to grow. We're just throwing fertilizer all over. Okay. So the first of all, I should have said this before, but if you start with a contact form, you multiply it by any positive smooth function, you get another contact form. So you can just check that from the definition. The Reeb vector field might be very different, however. So if you multiply the contact form by a constant, you'll have the same Reeb vector field, it will just be rescaled by the inverse of the constant. Otherwise, the direction will change. So that's what Uriah's closing lemma is saying. So here's Y, and here's some neighborhood, let's call it U. I want to have a contact form, and there are no Reeb orbits that go through U. So U is feeling sad. It's like a town with no road going to it. So the economy is really suffering. And they're saying, all right, we have to do something about this. So now you take this function f, and it's supported inside of U. And then saying, all right, well, for some t, the Reeb orbit will appear going through U. What's kind of remarkable is you only have to change the contact form inside of U. So it's sort of like changing a little bit, sort of how you're sort of leaving U, and well, actually, it's not changing that. Anyway, it's changing what's happening inside of U. It's making a Reeb orbit appear. So you can. This is actually an amazingly strong result. You can compare with Pugh's C1 closing lemma, which is from the 60s. Well, it's a more general statement, but in this context, what Pugh's closing lemma would say would be that I can make a C1 modification of the vector field to arrange a periodic orbit going through. A C1 small modification to arrange a periodic orbit going through U. And you have to do it very carefully. You have to very carefully modify the vector field on all of Y to make this periodic orbit appear through U. And Uriah is saying, you don't have to be careful at all. Just like throw some fertilizer, something will grow.
Is it supposed to be that the smaller the neighborhood, like the bigger the you're making it go so fast that like it's, or is that just the wrong?
Okay, yeah,
That's
so
what
that
it looks
actually
like to me.
leads into my next result I was going to say. Thank you. So you can say, all right, like, suppose I want this, the period of this to not be too big. How much do I have to change the contact form? So that, thank you very much for that question.
You asked me to ask that.
Sorry?
I said you asked me to ask that. I didn't know.
Audience.
So this leads to what you call a quantitative closing limit. I'm sorry, we have that for this. So the question is, so given some L, some positive real number, how much, I'm going to put this in quotes because we're going to have to come up with a definition of what this means. But how much do we need to change lambda to obtain a Reeb orbit intersecting some given neighborhood U, let's say in U. With period less than or equal to L. So you would think that if I want the period to be shorter, I'm going to have to make more of a change. I can tell you the approximate answer is O of 1 over L. Now, sorry?
So what for what measure and how much?
So now let me make a more precise statement. So definition. Positive information of lambda supported in U is a one parameter family contact forms e to the ft times lambda, where g goes from 0 to 1, such that f0 is identically 0, f1 is bigger than or equal to 0, f1 is not identically 0, and the support of ft is contained in U. So I'm changing the contact form, I'm only changing it inside of U, and at the end of the day, it's a non-negative function. And then there's a notion of the width. So I don't have time to fully explain this, but just, so this is maybe more for the experts. So this is the row of width of the set of S comma Y in R cross Y with the symplectic form omega equals d of e to the s lambda, such that 0 is less than s is less than f of y. So basically, inside the four manifold r cross y, if this is the r direction, then I have a copy of y where the r coordinate is equal to 0, and then I have the graph. Oh, sorry, this is f1. I have the graph of f1, which looks like this. And in between these, there's some region. And the growth width is the largest size of a ball, which can be symplectically embedded into here. So anyway, I'm really running out of time. Okay, so I need to state my theorem. Anyway, some measure of the size of the deformation, which works for the theorem that I'm going to state. And we can at least, it's not necessarily computable, but we can at least bound it. So then I need one more definition, which is that, so close L of y comma lambda is the infimum of delta such that, so delta is a non-negative number, such that for all open sets u and y, for all positive deformations, e to the ft lambda supported in u with width bigger than or equal to delta, there exists t in 0, 1 such that e to the ft lambda has a Reeb orbit intersecting u with period less than or equal to L. So it's kind of a complicated definition. I'm sorry that there's not that much time. But basically, so the summary of what this number means is closed L is how much do I have to change the contact form to be guaranteed to create a periodic orbit period less than L. And maybe this infimum is infinite, and then I sort of wouldn't have anything. The theorem.
What do you call that? Close L. What is?
That's a y. So it depends on the three manifold of the contact form.
Closing,
Close as
lemma,
in close.
L, length.
Got it. Yeah.
So theorem. So the lim sup of, as L goes to infinity of L times close L of y lambda is less than or equal to the integral over y of lambda wedge d lambda. So this is the general quantitative closing lemma. This is sometimes sharp. Some can compute this in examples like the ellipsoid from before. So basically it says close L is less than or equal to 1 over L times some constant. I didn't have time to talk about the technology which goes into this, so sorry for that. But if you look at I have an archive preprint from 2022, which was published in Journal of Modern Dynamics. It has quantitative closing lemmas in the title. If you look at that preprint, it explains the technology used to prove this. Thank you.
Okay. So, any questions?
So in the examples where there are at least 3 orbits, we know there are infinitely many. How many infinitely many? Like asymptotically as you let the period grow. Like in a lot of these examples, we know much more.
Right, that's a great question. So, in some cases, I can prove that the Reeb flow is positive topological entropy, which implies that the number of orbits, the length period less than or equal to L grows exponentially now. In some cases, it's not true. One could conjecture that it grows quadratically. But we can prove some like very poor bound on the growth rate, but I don't know very much about that.
How do they like distribute with respect to the measure induced by the Reeb
So Erie
or the contact form? Sorry.
Yeah. So if you want to say how do all of the Reeb orbits distribute, I have no idea. So K. Erie proved refinement of this result, which says that you can at least find a sequence of Reeb orbits which are equidistributing in certain sets. And then there's related work in minimal hypersurfaces by Andre and others. There's actually a lot of, I didn't have time to go into this at all, but there's a lot of parallels between this story and people know about minimal hypersurfaces. But yeah, in general, like, if you want to say how do all 3 orbits distribute, I have no idea. It's a great question.
And do you have examples where you get strict inequality in the limb soup you wrote?
Yes. So these numbers close L could all be 0. So that happens in cases where every point is on a Reeb orbit. For example, if I took the ellipsoid, if I said A over B is rational instead of irrational, then all these numbers would be 0.
Okay, any other question? Okay, if not, let's thank the speaker again.